Good morning, everybody, in pre-calculus and trigonometry land. Just to get us started for the week this week, we have sort of two topics that I want to touch on today. Excuse me. The first is to continue some of the work that we were doing with trigonometry last week by exploring a little bit more in depth what our author of our textbook calls the process of finding angles. So using the inverse trigonometry that we were learning at sort of the level of functions when we talked about them last week, and apply that more to the process of finding angles. So that's section 4.4. We're going to look at that today. And then also we'll talk some about the process of looking at the end behavior of power functions. So limits, infinity, and how powers of x work as functions. So before we do that, are there any questions from those of you that are participating today via Zoom?
Professor?
Yes.
Is there any way before we start we can go over 4b on quiz 6? It's negative log p and then in parentheses 2/7. I'm just a little confused on because it also says use properties of logarithm to rewrite each of the following using a simple log with a coefficient of 1.
Well, let's do a quick topic, a cleanup topic before we start today. I want to take a look at the quiz that was just due the other day. We're going to look at problem 4. This was one of the properties of logarithms style questions, and just want to talk specifically about part B. So we'll do that just to get us kicked off here. Let me pull up a copy of that quiz. Let's see here. It's the quickest way for me to get to the quiz. Let me head into Canvas and go into the assignments. Over to quiz 6. Okay. Zoom in on this a little bit. All right, so let's take a look at this problem from the quiz from this past week. Zoom in a little bit so we can see it as well as possible. Okay, so here's what the problem looks like. The problem asks us to use the properties of logarithms to rewrite several expressions using a single log with a coefficient of 1. So the purpose of this is to just get us some more practice with using the properties of logarithms to do these rewriting processes. And the question I specifically want to look at is the one right above my head here, minus the log with a base of p of 2/7. So let me copy that down on a separate sheet here, and we can take a look at it together. 2/7. Okay. So if I want to simplify this expression in a way that, according to the instructions in the problem, gives us a single logarithm with a coefficient of 1 in it at the end of the day, there's a couple things that I could do. I could worry first, perhaps, about the arithmetic inside of my logarithm, that division sign that's sitting right there. There's something that we could do with that because we know that logarithms, if we go over to our handy-dandy logarithmic properties chart that we've been working off of. Sorry, let me try and get that up on our screen here real quick. There we go. So we have properties of logarithms that tell us, for example, what we can do with a division inside of a log. Division on the inside of a log, if we bring it out, can turn into subtraction on the outside. So that's one option for what we could do in this expression. The other one is to use the thing that's behind my head right here, which, let me just get my hat out of the way, that if I have a power on the inside of a log, that exponent can be brought out as a multiple on the outside of the log. And we could use this as well, because we actually have both of these things going on inside the expression that we're trying to simplify. I've got division going on the inside, but then on the outside I also secretly have this minus sign, which is the same thing as a multiple of -1. So either one of those two I could decide to do first. I think the version that I prefer is let's deal with the multiple on the outside, that -1 that's on the outside. So according to our log properties, again, getting my head out of the way, if I have a -1 that's playing the role of that y on the outside of my logarithm as a multiple, that multiple can be brought into the log as an exponent. So what I'll do is I'll bring that -1 inside my log as a power on the argument of my logarithm. So what I'll have then is I'll have the log base p of 2/7 to the power -1. Now, what does it mean to raise something to a -1 power? As we'll remember from our properties of exponents, one of the ways of understanding how to do that is to distribute that -1 power to the numerator and the denominator. If we do that, we end up with a 2 to the -1 and a 7 to the -1. But then, again, using our properties of exponents, we can rewrite those using positive exponents instead of negatives by transplanting those powers from the numerator to the denominator and vice versa. So trade out multiplication for division. So a 2 to the -1 power on the numerator of a fraction is the same as the 2 to the +1 power in the denominator. Same thing for the 7 to the -1 in the denominator is the same as 7 to the +1 in the numerator. So another way to see this is just to see it as 7/2. So to raise something to the -1 power is nothing more than just to take its reciprocal. And if I restore my logarithms in their proper places here, then here's what I have. Log base p of 7/2. And this is the point where if I read the question prompt carefully, which is always a good idea. Did I lose it here? Yeah, if I read my question prompt to make sure that we're doing what's being asked here. Use the properties of logarithms to rewrite each of the following using a single log with a coefficient of 1. Actually, at this point, I think I would have to sort of dust off my hands and say this has done what the question has asked me to do. There's a single logarithm in this problem. It's a log with a base of p. And the coefficient in front of it is indeed 1. So if you got here on the quiz and you stopped, that follows the letter of the question that was asked. If you decided to take it further, I'll just put here optional. I won't begrudge you for this, because it's a good use of the properties of logarithms still. We can take this quotient, 7 divided by 2, that's happening inside of the log, and turn it into a difference on the outside of the logs. And so we could turn the log of 7/2 into the log of 7. Again, the log is with a base of p, minus the log of 2. That log with a base of p also. Again, the way that the prompt for this particular quiz question was written, you could decide to stop here if you so chose, and that would actually very explicitly sort of match what was asked. So there were kind of opportunities to use two different properties of logarithms in the process of solving this problem. All right. So I want to, sort of as we usually do, talk about our trigonometry stuff last. I'm going to try to save some time for it. I've been kind of bad at that the last couple of class meetings. And before we get there, what we will do in our first portion of today's exploration is just get an introduction to the beginning of the fifth chapter. This is the last new chapter that we're going to meet in our textbook for this semester. It's a chapter called Polynomial and Rational Functions. So that's our last topic that we cover together. And the central player on the stage of polynomial and rational functions are functions that are built on powers of x. So we just finished the chapter on exponential and logarithmic functions where that variable, my unknown, my x, tends to be an exponent, e to the x, 2 to the x, or it tends to be trapped inside of a logarithm function, right? Now we're going to go back to what's probably going to feel like more familiar types of algebra because our x's, our unknowns, are going to be the base now, and the exponent is going to be a number, a constant. And those powers of x, where that constant up there can be positive, it can be negative, it can be a fraction, it can be an irrational number. Most of the time, though, when we talk about polynomials and rational functions, by definition, those are going to be functions that are built off of integer powers of x. So x to the 2, x to the 10, x to the 17, x to the -5, x to the -12, x to the 0, and not things in between like x to the 0.5, because that would be a radical function. So polynomials and rational functions are built out of building blocks that are just powers of x in one way or another. And so the first thing that we're going to do in this chapter is sort of wrestle with the question, what do powers of x, just a single power of x, what does that look like as a function? What can we say about the properties of a function whose formula is defined using a single integer power of x? That's the big question. What do the behaviors of those functions look like? And in particular, in this first section, we want to spend our time thinking about the behavior that mathematicians call the end behavior. End behavior is an answer to the question, what happens to the value of the function as the value of its input gets really large, so as the x that we put into my function tends toward infinity, or gets really large in the negative direction, so as x tends to negative infinity, going the other way. What is ultimately going to happen with the output values as ultimately my inputs blow up to plus infinity or blow up to minus infinity? Those are the big questions of this section, because if we understand what happens with a single power of x, it's then going to be a relatively small jump for us to figure out how functions that are built on multiple different powers of x, the polynomials and the rational functions, how they behave. So let's start this out, as we always do in this text, with the preview activity. So the preview activity for this section just asks us to get our head back into that end behavior space again, and think about what happens to the values of various algebraic expressions as their inputs, as the variable tends to positive infinity or tends to negative infinity. And we're introducing here a notation that we're going to hang on to for the rest of this chapter, and then you're also going to use this notation frequently in your calculus class when you get to calculus next semester. And so what this notation is sort of asking is, as the value of t gets very large, so as t tends to positive infinity, what is the value of e to the minus t going to be doing ultimately? As t gets really large, what happens to e to the minus t? And so what we're being asked to do in this activity is to try and do this reasoning without resorting to a graphing tool, but rather using what we know about the shape of the graph of this function. So when we first learned how to graph exponential functions, we graphed functions like f of t equals e to the minus t. And if you remember, let's just sort of reminisce about that one again together. The graph of f of t equals e to the minus t is going to be an example of, well, I guess the question we would ask ourselves is, what kind of a function is it? It's definitely an exponential function, right? It fits that model, right? It fits the y equals a times b to the x kind of model, right? Where the role of a here is being played by the coefficient that's out in front of the e to the minus t, and that a is equal to 1. And the role of the base, b, that's the thing that's being raised to the power of x, where x is my independent variable. But in this example, e to the minus t, another way to think about what e to the minus t is we can think of it instead as e to the minus 1 times t. I can just put in that minus 1 times there, right? But then if I do that, I can use the properties of exponents to turn that into e to the minus 1 quantity raised to the t. In other words, I could understand this as, what's e to the minus 1? Raising something to the minus 1 power is nothing more than taking its reciprocal, as we saw in the example from the quiz question that we talked about at the outset of today's video. So the base of this particular exponential function is 1 over e. Remember, e is just some number, 2.71828. It's this constant. And so if I take 1 over e, I'm just looking at a number that's about 1 divided by 2.71828 and so forth. So if I ask a calculator for a decimal approximation of that, I get something that looks like about 0.368. So I'll just sort of put that there. It's about 0.368. So what does all of this mean? Well, remember, the value of a in an exponential function tells me the vertical intercept for that graph. And so since we have 1 as the value of a here, that must mean that my graph is going to go through the vertical intercept of 0, 1. And then the value of b tells me the base of my exponential function. And since the value of this base, 0.368, since that base is less than 1, that means that this function is an example of an exponential decay function and not an exponential growth function. So where exponential growth tends to go up without bound as x tends toward positive infinity, exponential decay tends to do the opposite. Right? It tends to decrease down to the x-axis as x tends out to positive infinity. And so we have an example here of exponential decay. I'm only talking through this first example a lot just to get our heads back into the exponential space for a little bit. Okay. But the fact that this is exponential decay means we know now what the graph is going to look like. Starting from its vertical intercept, it's going to go downward. And it's going to sag down towards the x-axis as x tends out to positive infinity. And if we were to rewind the tape and let x go the other direction, that's the direction in which my exponential decay function is going to grow instead. It grows in backwards time instead of in forwards time. So here's a graph of f of t equals e to the minus t. And so the question that's being asked here is, what is happening to the y value, if you like, right, the f of t value? What is happening to the f of t value as the t value tends out towards infinity? So as we go all the way out to what I call the rightmost horizon of this graph. So if we were to follow this graph out infinitely far toward the right side, what would be happening to my y values? Well, notice my y values, they start out as large and positive, but they're always decreasing. They decrease through this point at 1, then they continue to decrease and decrease and decrease and decrease. But what is ultimately happening to those y values? Those y values are getting smaller and smaller, but they're never ever getting negative. And they're also never ever becoming actually 0, but they do get arbitrarily close to 0. So what we would say is that as t approaches positive infinity, the value of f of t, my y value, is approaching the value 0. That 0, again, coming from the fact that it's the x-axis which has the equation y equals 0. That's the horizontal line, the horizontal asymptote, remember we called it that, toward which this function tends as t goes out to infinity. So that's how we would fill in this blank here. As t goes out to positive infinity, e to the minus t tends to 0. Let's apply that same reasoning to fill in the rest of these blanks just to get us sort of warmed up with what end behavior is and how we can think about end behavior for functions. Let me clear up some space. Because again, we want to do this reasoning just using what we know about the graphs of the various functions involved. Let's look at the next example. What about the natural log function? Well, the natural log function is nothing more than the inverse of the exponential function f of x equals e to the x. And so the graph of my logarithm function is going to look something like this. It tends to a vertical asymptote on the y-axis. But as x tends out, or sorry, as t, I guess is our variable here, as t tends out to positive infinity, what are my values of f of t doing? They are increasing, increasing, increasing. We think without bound. One of the ways that we could investigate that, I know it tells us not to use technology and those sorts of things, but we could conceivably use some technology to try to investigate a question like this. Let's see what would happen if we tried taking that tack real quick. So I have the function f of x equals a natural log of x. I can plug numbers into that function. And if I plug numbers in that get increasingly large, so if I plug in a 5, I get a value for f of 5 is about 1.6. If I plug in a bigger number, f of 50, natural log of 50, that turns out to be 3.9. So it's bigger than f of 5 was, which is not particularly surprising because we know natural log, like all logarithm functions, f of x equals log base a of x, all logarithm functions are increasing functions. But is this trend going to continue? And to what extent does it continue? So let's keep going. What about 500? If I plug a 500 into my function, natural log of 500, about 6.2. Okay, so we're still increasing. So the question we want to be asking is, how far does this trend continue? Do we continue to increase without bound? Can we make this number, this y value, as large as we like just by picking my input, my x, to be as large as we need? So if I put an even larger number in there, I get an even larger number as my output. If I put 8,675,309 into my log function, I get 15. So it looks like the bigger, we can make these numbers bigger and bigger and bigger. And by making the inputs bigger and bigger, the outputs get bigger and bigger. And we think that there's no ceiling on that, that continues to increase without bound. But the only real reason that we can be assured that that does in fact happen is we can remind ourselves, what is the range of the natural logarithm function? It's going to be that portion of the y-axis, the vertical axis, that the graph of the natural log function covers. Right? Well, if we're unsure whether the range goes all the way out to positive infinity, right, we may as well ask the question, well, what about the domain of the exponential function? The inverse of the natural log is the exponential function f of x equals e to the x. And the domain of the inverse is going to be the same as the range of the original function. So the range of natural log is the same set as the domain of the exponential function. Well, what do we know about the exponential function? Its domain is all real numbers. So here's my exponential function, right? Looks like this. And since my domain of my exponential function extends out to positive infinity, I can take e to the x for any value of x from negative infinity to positive infinity. That must mean that the range of its inverse, the natural logarithm, also extends from negative infinity to positive infinity. And since my function is increasing, that must mean that it is therefore increasing without bound. Even though it looks like it kind of increases pretty slowly, right? It took us some really large inputs before we even started to get outputs of things like 15 and 16, right? Even though it tends to increase very slowly, it does, in fact, according to our domain and range swap, it does, in fact, increase without bound. So as t goes to positive infinity, the natural log of t also tends to positive infinity. It increases without bound. And it's for some of the same reasons that we can answer things like, as t goes to positive infinity, e to the t goes to infinity. As t tends to 0, e to the minus t tends to its vertical intercept, which is 1. This is an interesting one. What happens as t goes to infinity with 35 plus 53 times e to the minus 0.025 times t? Well, as t tends to positive infinity, if I multiply that t by a number, negative 0.025, that number, negative 0.025 times t, is going to tend to negative 0.025 times infinity. That number in the exponent is going to tend to minus infinity. So another way to think about this is to just think about this exponent here as being like a minus infinity. Well, what happens if I take the exponential of a very large negative number? What's happening to e to the minus t as t tends to infinity? According to our answer to part A, this e to the minus infinity, that's the what e to the minus t tends to as t tends to infinity. According to part A, that tends to 0. And since that part tends to 0, multiply 0 by 53 and get 0, add 35, and we'll conclude that this is 35. Right. So we're kind of doing some loose sort of heuristic kind of analysis here. When you get to calculus, you end up learning this as a concept. It's sort of the central concept in all of calculus. It's called a limit. And it's an answer to the question, what does the output of a function tend toward as the input to that function tends toward a selected place, right? And so we're sort of, reasoning broadly about limits here. We're not doing it in any particular, we're not adding a level of sort of algebraic and logical rigor to it that you will when you take calculus. But questions like these consume a lot of your thought in calculus, and they really unlock a lot of the power of what calculus can help us to do. So with that under our belt, what I want to do is look at the questions that are asked in the activities in the rest of the section for this section on limits, powers, and infinity. And the main questions that we're interested in sort of addressing in this section are questions similar to the ones that we just talked about with the exponential and logarithm functions, but applied instead to functions that are built on single powers of x. So what is the end behavior of functions like f of x equals x to the power minus 1, x to the power minus 2? What about x to the positive 2, x to the positive 3, and so forth? What do those functions have in common as far as their, let's call it the local behavior? What do they look like as x goes toward 0? And then also their end behavior. What do they look like? How do they behave as x tends to plus and minus infinity? Let's first address the question about positive powers of x. So this question is addressed in the Desmos worksheet that's actually linked in this section of the text. So I think that's a good place for us to start. Excuse me, to start this this portion of what we're looking at. So the question here is, if I think about the functions f of x equals x raised to a positive integer power. So that includes x to the power 1, x to the power 2, x to the power 3, 4, 5, 6, 7, 8. What do those functions have in common as far as their behavior near x equals 0? And then what do they have in common as far as their behavior as x tends out toward positive infinity? So here on our screen right now, we are looking at f of x equals x to the power 1. f of x equals x. This is the diagonal line graph, y equals x, right? Let me expand that out a little bit just so we can see it a little bit better in the video. But then what happens as I increase that exponent? F of x equals x squared is our familiar parabola graph, right? F of x equals x cubed is the cubic, x to the 4th, x to the 5th, x to the 6th, x to the 7th, 8th, and so forth, right? If we wanted to, we could even sort of extend this. Let's keep it going out to x equals 50. And then sort of see what happens. So we start at x equals, f of x equals x to the power 1. And as we increase that exponent, take a look at how the graphs are changing, right? I'm just going to have it go to the end and stop here. So what can we say about what these graphs have in common, and then maybe what sort of separates them one from another? Whoops, something got screwed up here. Let's just go from 1 to 20. I think the first thing that I would say, that I'm noticing, is that one thing that they all seem to have in common is that all of them have the same vertical intercept. All of them go through the point 0, 0. That's not, I hope, too controversial of a statement. And that's not too surprising either, I hope, because if x is equal to 0 and I raise x to a positive integer power, I'm taking 0 to the power 1, 0 to the power 6, 0 to the power 17. And any positive power, any positive exponent on a 0 for the base is always going to give me 0, right? It's 0 multiplied by itself a certain natural number of times, right? And so the fact that they all have the same y-intercept, 0, 0, hopefully not too surprising, but that is something that all of these functions have in common. What else do they all have in common? Well, if I sort of back it up a little bit, let's think about their end behavior. Not what's happening as x tends towards 0, as my input values become very small, but what's happening as my input values become very large, as x goes all the way out to the rightward horizon of the graph paper. Turn off my grid here real quick. Maybe I'll even turn off the numbers on the axis, so we can focus just on the shape of the graph. Let's ask first about what's happening as x tends to positive infinity. So as we go to the rightward horizon of this graph, what's happening? Well, x squared, f of x equals x squared, that seems to tend to positive infinity. As x goes to infinity, so does f of x, the value, my y values. As my x values go all the way to the right, my y values go all the way up without bound. And that remains true for the cubic, for the quartic, for the quintic, and so on and so on and so on. Now don't be fooled, it kind of looks like the graphs here become almost vertical. So it sort of suggests like there should be an asymptote here. But the fact is, what we're seeing is that this growth, the rate at which this function is growing towards infinity, is just getting so fast that we can't see enough of it in my window before it just ends up escaping so quickly up to infinity. But the domain of all of these functions, of all these power functions, is all real numbers. And so we know that this graph exists above every single point on the x-axis. And therefore, there are no vertical asymptotes that we would need to worry about. These functions are indeed blowing up to infinity as x tends to positive infinity. So that's something that all of my positive integer power functions have in common. What about the other horizon? So as x tends to negative infinity, what's happening? So f of x equals x. So if I start at the first power of x, As x tends to negative infinity, so as x goes out to the left end, the left horizon of the graph paper, the y values are tending downward without bound. So the y values go down to negative infinity as x goes to negative infinity for f of x equals x. But for f of x equals x squared, it looks like we're flipping, right? Now as x goes to negative infinity, f of x tends instead to positive infinity. One of the reasons that that shouldn't be a surprise is that f of x equals x squared, because it's an even integer power of x, we cannot ever get a negative output from this function for any real input that we give it. The square, the second power of any real number, is always non-negative. We can't square a real number and get a negative answer. And so there's no way that this function could tend toward minus infinity, because in fact, the output values of this function never become negative at all. But the shoe's on the other foot again for the cubic function, because my odd integer powers do respect sine. If I put a negative number into my cubic function and I multiply it by itself 3 times, negative times negative times negative is going to give me negative, right? And so for f of x equals x cubed, as x tends to negative infinity, f of x also tends to negative infinity. And that's why we're seeing this funny sort of tail wagging behavior as we increase my exponents, right? Every even exponent, we're going to have, as x tends to negative infinity, we're going to tend to positive infinity. Every negative exponent, as x tends to negative infinity, f of x tends to negative infinity as well. So let's use this opportunity to just kind of summarize so far what it is that we know about the powers of x and what they have in common for the positive exponents. I'm going to switch back over into my whiteboard. So for my positive exponents, for n greater than or equal to 1, we have that f of 0 equals 0 to the power n. That's equal to 0, right? All of my graphs went through the origin in the example that we just did. And we also saw that in all of these examples, as x tended to positive infinity, f of x also tended to positive infinity. That was the end behavior of my positive integer powers of x. They all blew up to the north as we went out to the rightmost horizon, the easterly horizon of the Cartesian coordinate plane. It was the western horizon, as x tends to negative infinity, where we saw some mixed behavior, right? Where we needed to know whether my exponent was even or whether my exponent was odd. So when my exponents were even, f of x tended to positive infinity. And when my exponents were odd, f of x tended to negative infinity. So there's what we can say as far as what the positive integer powers of x, what those functions all have in common one with another. So what's good for the positive integers is good for the negative integers too, right? No, that's the question that we want to sort of approach next. What happens with the negative power functions? So the first of those negative power functions is f of x equals x to the power minus 1. This is also known as f of x equals 1 over x. We call it the reciprocal function. If we take a look at the reciprocal function, if we graph y equals 1 over x, let's take a look at what that graph ends up looking like. This certainly looks qualitatively very different than the graphs that we saw in our previous few examples, right? F of x equals 1 over x has this sort of curvy shape, right? It seems like it kind of escapes, it crashes through the floor as we get closer to the x-axis. Sorry, closer to the y-axis, I guess, over here. It crashes through the floor, and then it reappears out the top of the ceiling. And it looks like as we go out to the rightmost horizon of this graph, it looks like the graph is sort of settling down to the x-axis. And also, as we go to the leftmost horizon of this graph, the same is also true. It's kind of settling in on the x-axis, no matter whether we go out to the easternmost or the westernmost horizon. I'm pointing the wrong way, easternmost or westernmost, right? So this is f of x equals 1 over x. And another thing that we notice is that this function, this graph, has no y-intercept at all. And it has no y-intercept because there's no point on this graph that has an x-coordinate of 0. Why not? Because if it did, what is 0 to the power negative 1? It's undefined. Why is 0 to the power negative 1 undefined? Because to raise a quantity to the negative 1 power, remember, it's the same as trading multiplication for division. It's the same as 1 over 0. And 0 is the only real number by which we cannot divide and receive any answer at all, right? 0 as a divisor makes any division problem have an undefined answer. And so y equals 1 over x does not have x equals 0 in its domain. And in fact, that's the only value of x that is excluded from the domain of y equals 1 over x. And that same thing is going to be true for all of my other negative integer powers of x. After all, x to the power minus 2 is the same as 1 over x squared. And again, if I were to plug a 0 in for x in my denominator here, we would again get an undefined result because it would evaluate to 1 over 0. So maybe that's one of the next sort of commonalities that we can kind of notice for all of my negative integer exponents, powers of x. Let's switch back over to the whiteboard. For my negative n's, n less than or equal to 1, f of 0 is undefined. In fact, the domain of any of my f of x equals x to the n functions, where n is a negative integer, my domain is going to be the set of all x's, all real numbers x, such that x is not equal to 0. 0 is the only real number which is excluded from the domain of my function. And we can again see that from the graph. If you imagine this graph being squished onto the x-axis, how much of the x-axis is going to be covered? Well, there's going to be one point, and only one point, that is missed in that process. That's the point at x equals 0. So we'll color that as an open circle. But every other point on that axis does, in fact, get hit as an element from the domain. So x not equal, does it let me do that? X is not equal, no, I guess it doesn't let me use that syntax. All right, so we'll understand what this graph means here, right? So the domain is the entire x-axis with the exception of x equals 0. And that's true, again, for all of my power functions, that is the case. Okay, so let's ask the next question. If we start to increase this exponent, if we start to look at x to the minus 2, x to the minus 3, x to the minus 4, what's going to remain the same and what's going to be different about these various functions? So let's just hit the play button and sort of observe and see what happens. So as I go from n equals 1 to n equals 2, we're still missing that one point in the domain. But take a look at what's happened. This piece of the graph, which used to be in the third quadrant, for f of x equals 1 over x squared, that piece is now in the second quadrant. And if we go back to 1 over x to the third, it goes down to the third quadrant again. Second quadrant, third quadrant, second quadrant, third quadrant, right? And so it does look like there's some commonalities in the shapes of these graphs. But again, there's kind of an important difference between those where the exponent is a positive, or sorry, where the exponent is an odd integer, and those where the exponent is an even integer. So let's try and quantify those things. But first, let's again return to the question, what do these all have in common? And what it looks like they all still have in common is they all have the same end behavior. As x goes out to plus infinity or minus infinity, so if we look toward the rightmost horizon of this graph, as x tends to positive infinity, the value of f of x, the y value, settles down to the x-axis. In other words, it settles down to 0. Does that trend continue for the other exponents? It sure looks like it does, right? Even 1 over x to the 8th has this property that even though some crazy stuff is happening in here close to x equals 0, as x gets out to positive infinity, as we scroll out to the rightmost extent of this graph, the y values are settling down to 0. And the same remains true also on the left side. As we scroll out towards x equals negative infinity, no matter what my exponent is, my negative exponent is. No matter what that is, it looks like the values are again tending towards 0. So back to the whiteboard for a second. Something that all of these have in common is that as x tends to positive infinity, f of x is tending to 0. And also, as x tends to negative infinity, f of x is going to tend to 0. So these negative powers of x functions approach the x-axis in both the leftmost and the rightmost direction. Right? They sort of settle down to the x-axis regardless of what exponent that I might be choosing. So how do we use the notation that we're picking up today to describe this new sort of tail-wagging behavior that we see happening here, where the power functions with an odd exponent seem to do something different than those with an even exponent? How do we use the notation to sort of quantify, to communicate that? Well, let's again think about this as an x approaching problem. I'm going to take the x to the third power example here. Actually, what I'd like to do is I'm going to draw my own version of this graph just so that we can sort of look at it. I want to be able to draw on it, but I can't draw on my browser window right now. So all right, so here I'm just going to put it on my whiteboard over here for a second. So this is f of x equals 1 over x to the power 3. Not a particularly accurate graph, but it captures the basic shape well enough for me to make the point that I want to make here, which is how do we understand the behavior that's happening here and there? Okay. What it looks like, and this is ultimately going to be the language that we're going to use to describe this phenomenon, what it looks like is that there's a vertical line that this graph is sort of infinitely closely, arbitrarily closely approaching. And indeed, the closer that x gets to 0 among the positive values of x, the closer that corresponding point on the graph is going to get to this vertical line, which also happens to coincide with the y-axis. And the same thing is true on the negative side as well. Let me try and clean up this graph a little bit. That the closer that my negative values of x get to 0, the closer that the corresponding point on the graph of the function is going to get, again, to the y-axis. And so the y-axis is this sort of line, the y-axis which has the equation x equals 0, remember, is this line that my graph can approach arbitrarily closely, but it never actually touches it or crosses it. And we know it never touches it or crosses it because if it did, it would have to do so at a point with an x value of 0, but the x value of 0 is exactly the only value that is not a part of the domain of my function. And so there cannot be a point on this graph whose x-coordinate is 0. And so we call this a vertical asymptote, just like we did for the natural logarithm function. Had a vertical asymptote. Natural log had it because the exponential function, which is its inverse, happens to have a horizontal asymptote. Why does this function have a vertical asymptote? That's going to be one of the kinds of questions that we're going to address as this chapter goes along. For now, let's just be content to use the notation that we're learning today to express this vertical asymptote, just to communicate it. Right? So how we would say it is probably something like the following. First, let's look at the right-hand side of this piece of the graph. Right? On the right-hand side, what we might think of is taking a sequence of points that are getting sort of closer and closer to that vertical asymptote. So here's how I want to think about it. I want to sort of take a bunch of points along this graph that are sort of getting closer and closer to that asymptote. Those points are going to have x values. And the x values of those points are going to be getting closer and closer to 0 in the positive direction. Right? There's one more there. So what I might say is something like this. I'm going to try to draw this in a way that's as illuminating as possible here. So as my x's get closer and closer to 0 from the right side, so as my positive values of x get closer and closer to 0. And that's a piece of the notation that was part of the preview activity that I didn't really go into depth on, but now is a good time to do that. So as my x values get closer to 0, but they do so from the right side. So we'll use this little plus up here next to the 0 to communicate that we are thinking about positive values of x here. And so often, particularly in your calculus class, you'll read this plus in English by saying from the right. So from the right side, as x approaches 0 through values which are greater than 0, okay, what can we say about the y values? And so now is when we turn our attention to the y values of these points. What's happening to them? Well, the first point right here has a y value that's approximately that much, and then my next point has a y value that's this much, and then this much, and this much, and this much. So my y values, evidently, are going up and up and up and up. So as x approaches 0 from the right-hand side, what we can say is that f of x is approaching positive infinity. As we get closer and closer to x equals 0 from the right side, the y values of my points, the values of my function, my outputs, are increasing without bound. So, coming back to this, what we would say is something like this. Let me try and write this down. So, as x approaches 0 from the right side, f of x apparently approaches positive infinity. Coming back to the graph for a second. That was true for f of x equals x to the power negative 3. It also looks like it's true for x to the power negative 4. Again, remember, we're just looking at the right side of this graph. X to the 4 looks like it does it, x to the 5 does it too, x to the 6 does it too, and so on and so on. So it doesn't appear to matter whether my negative exponent is even or odd in this example. They're all blowing up to positive infinity, all these functions, as x tends to 0 from the right side. What about from the left side? As x tends to 0 through negative values, what is happening to the values of f of x? Well, for my one we were looking at in the beginning, f of x equals x to the power minus 3. As x tends to 0 from the left side, f of x is tending to negative infinity. Right? It's crashing through the floor. But 1 over x squared, when my exponent is a even integer, as x tends to 0 from the left side, f of x, the y values, are crashing through the ceiling instead of the floor. And so now here we do have this tail wagging behavior that we were seeing in my positive exponent, positive integer exponents. Before we saw this tail wagging happening as x goes to minus infinity. Now we're seeing it happening as x tends to 0 through negative values. That's not an accident. After all, replacing x by 1 over x is the same thing as changing one of these negative exponents to positive. And doing that exchanges sequences of x's that tend to infinity for sequences of x's which tend towards 0. Because if I take the reciprocal of a number that's very, very, very large, the result is very, very, very small, i.e. close to 0. And so that same behavior that we saw as x tends out to negative infinity in my positive integer powers, this tail wagging, when I take the reciprocal of all of my x's, it becomes this tail wagging as x approaches 0 from the left side. So just to quantify it, it appears that when when n, my exponent, is even, that's when we tend to positive infinity as x tends to 0 from the left. And when my exponent is odd is when f of x tends to negative infinity as x tends to 0 from the left. And again, it shouldn't take too much grappling to figure out why that's the case. Right? If I take 1 over x, for example, so let's go back to that original example. As x tends to 0, my denominator here is going to get closer to 0, and so the value of 1 over x, the reciprocal of something that gets close to 0, is going to be something that's very large. But since x is negative when we're tending to 0 through negative values, this fraction, 1 over x, is going to be a negative real number. And so we're tending to negative infinity here. Whereas with 1 over x squared, my fraction is still looking like 1 over 0. It still looks like it's blowing up, right? It's going to some kind of infinity as x tends to 0. But when x is negative, x squared is still positive. And so in this fraction, 1 over x squared, those are going to be positive large numbers. And so that's why these graphs tend to positive infinity instead of to negative infinity. So just to sum this all up, as x tends to 0 from the left side now, okay, so we're looking at the left side vertical asymptote, we know that f of x is going to tend to positive infinity when n is even, and it's going to tend to negative infinity when n is odd. And what you might notice, or at least what I notice in everything that we just sort of drew here, are the parallels. Right? And I hinted at this a minute ago, that same sort of thing that happens in my positive exponent cases, when x tends to positive infinity, is the same thing that happens when in my negative exponent functions, I'm tending to 0 through positive values. That's, again, not an accident, because in a way, positive infinity is kind of like the reciprocal of a positive 0. Please don't quote me on that. It's very back of the envelope. But again, one of the ways to understand that is if I have a sequence of numbers that are increasing to positive infinity without bound, their reciprocals are going to decrease to 0, arbitrarily closely to 0, through positive values. So as x goes to plus infinity, 1 over x is going to go to 0 from the right side. So that's why those two things correspond. Because after all, what if I substitute 1 over x in place of x in this function, 1 over x to the power n is the same as x to the power minus n. So it's the same thing as just changing the sign of my exponent. For that same reason, as x tends to minus infinity, so if I have a sequence of x values that decrease to negative infinity without bound, their reciprocals are going to approach 0 from the left-hand side. And from that perspective, it makes sense then, this thing that's behind my head is the same thing as the thing that's up here. F of x approaches positive infinity for even exponents and negative infinity for odd exponents. That's the same thing that happens here. Mathematicians that are a little bit more full of themselves would call this an inversion of the x-axis. When I replace x by 1 over x, I'm turning the whole x-axis inside out. And so every trend that we originally had seen, let me recenter my graphs here for a minute. Point at this. So any trend that we could observe in my positive exponent examples, like 1 over x to the third, if I just turn my x-axis inside out so that the zeros become infinities and the infinities become zeros, that's where we get the 1 over x to the third graph. Where now this graph sort of goes haywire at x equals 0 because this graph went haywire at x equals plus or minus infinity. And the same thing that this graph is doing at x equals 0, which is settling down to 0 at the origin, this graph is doing as x tends out to the infinities. It's settling down to 0. So we're just turning the whole x-axis inside out when we replace x by 1 over x. So there are some parallels. And I want to kind of wrap this up by saying the following. Once we understand just this basic set of information that's on this screen about how single powers of x, single integer powers of x behave, that is going to tell us almost everything that we need to know when we take our step into the next section and talk about functions that are called polynomials. Polynomial functions are nothing more than the sum and scalar multiple of positive integer powers of x. And even though there's potentially a bunch of different terms in a polynomial that have maybe different exponents on them, we can know what all of those terms are doing as far as their local behavior and their end behavior by what's on the screen right here. And similarly, when we move forward to talk about rational functions in the second half of our chapter, those are going to include the negative powers of x as well. And again, the stuff that's on this screen is going to help us to understand what's going on with those more complicated functions because we're going to be able to understand each of their individual building blocks. So I do want to take a few minutes at the end of our video, our class session today, to get our heads back into some more trigonometry, in particular the use of some more inverse trigonometry. So let's do that, just sort of take maybe 10 or 15 minutes and continue the discussion about inverse trigonometry that we started last week. And I'll do that today through, at least we'll start with the preview activity from section 4.4. In this preview activity, what they're asking us to do is to sketch a right triangle. And they've given us some information about that right triangle. And then we're going to use the measurements of that triangle to evaluate some inverse trigonometric ratios. So here's the plan. consider a right triangle that has one leg of length 3 and another leg whose length is the square root of 3. So since the square root of 3 is smaller than 3, I'll label this leg out here, which is a little bit shorter. I'll label that square root of 3, and I'll label the longer of these two legs 3. And it says, let theta be the angle that lies opposite the shorter leg. So the shorter leg is the square root of 3 leg, and opposite of that is the angle that's over here. So theta is going to be labeled this angle. Okay, so part A, sketch a labeled picture of the triangle. Done. What is the exact length of the triangle's hypotenuse? Well, for that, we know two other lengths in my triangle, and we're just looking to find the third length. And the single tool that we have in our toolbox for doing so is the Pythagorean Theorem. And so according to the Pythagorean Theorem, whatever the length of this hypotenuse is, if I call it C, for example, if I call the hypotenuse C, then according to the Pythagorean Theorem, C squared, the square of the length of the hypotenuse of a right triangle, is equal to the sum of the squares of the lengths of the two legs. And so if I square the two legs, they are respectively 3 and the square root of 3. If I add those squares together, I'm going to get C squared. 3 squared is 9. Square root of 3 squared is 3. So 9 plus 3, that's going to be 12. So 12 equals C squared. And then so C is plus or minus the square root of 12. But again, since we're doing geometry with a positive metric, we'll take the positive value. C is equal to the square root of 12. If you like, that's the same as 2 times the square root of 3. Okay, so we'll label that hypotenuse, 2 times the square root of 3. And one thing that I notice that jumps off of the page in my view of this triangle is that there's a nice ratio between the length of this hypotenuse and the length of this shorter side. The hypotenuse is in fact twice as long as the short leg in this triangle, which makes this one of the triangles that you probably learned about in your high school geometry class. This is a triangle whose angles are definitely 30, 60, and 90, because the hypotenuse is twice the length of one of the sides. But let's pretend that we don't know that for a second, because we're going to discover that in the process. In fact, I've kind of answered part E. Right here. What special angle from the unit circle is theta? It's 30 degrees, or pi over 6 radians. But again, we're going to suspend disbelief on that because I want this to also, this discussion to involve some inverse trigonometry along the way. So we did part B. Let's look at part C. What is the exact value of the sine of theta? Theta is this angle right here. Well, remember the definition of sine in right triangle trigonometry. In right triangle trigonometry, the sine is always the ratio of the length of the opposite side to the length of the hypotenuse. That's part of the SOHCAHTOA acronym that reminds us what the definitions of the trig functions are in the right triangle universe. So the length of the opposite side is the square root of 3. Again, it's opposite because it's the one side of the triangle that doesn't share a ray with this angle, right? And the length of the hypotenuse, well, the hypotenuse is opposite the right angle, right? Hypotenuse is twice the square root of 3. And so when I take that ratio, square root of 3 divided by twice the square root of 3, my square root of 3's can be reduced, and we end up with 1/2. So sine of theta is equal to 1/2 for this angle. Okay, so now they're asking us to do something. This is probably the trickiest part of this activity. Rewrite my equation from B, and my equation from B, I think they mean equation from C. There is an erratum for this exercise. Matt Belkins, if you're listening, rewrite your equation from C using the arcsine function. So, fortunately, we've been given a little bit of a hint here to kind of remind us how the inverse trigonometric functions work. Arcsine of blank equals blank, and in place of the argument here, we're just going to put this little square symbol. And in place of the other side of the equation, we're going to put a little triangle symbol. So we want to fill in the square in this triangle in a way that conveys the same information as sine of theta equals 1/2. So that's the equation from part C that this question is talking about, right? To what equation that looks like this is this equation equivalent? And all we have to do is remember that arcsine means, by definition, the inverse function of sine, where the sine function is taken to have the domain theta ranging from minus pi over 2 to pi over 2. So we restrict the domain of the sine function appropriately, and the inverse function of that restricted domain sine function is what we call the arcsine function. But as far as the algebra of this problem is concerned, that domain restriction isn't even important. All we really need to do, all we're really doing here is rewriting something that looks like f of x equals y. Actually, let me write that up here. F of x equals y. So we have some function f, which when I put x into that function, the output value is y. And we want to rewrite that in terms of the inverse function of f. How do we do that? Well, remember what inverse functions do. All they do is convey the same information, the same relationship as the original function, but with the roles of input and output transposed. Right? So all of my x's are now y's, all of my y's are now x's. Everything on the graph that used to be horizontal is now vertical. Everything that used to be vertical is now horizontal. All of my inputs are now outputs. All of my outputs are now inputs. My domain is my new range. My range is my new domain. You get the idea, right? At least I hope you do by this point. So all we need to do to convey the same information is to trade places with the y and the x, right? So if the sine function turns theta into 1/2, then its inverse must turn 1/2 into theta. And that's all that there is to this question. It turns 1/2 into theta. And so the equation we'll write that has the same logical force as the original is arcsine of 1/2 is equal to theta. But then, our noticing that this theta actually turns out to be one of our special unit circle angles that we've memorized the sines and cosines and tangents of, right? Because this is a 30, 60, 90 triangle from high school geometry. That meant that my angle theta was 30 degrees or pi over 6 radians. And so we have just computed a value for the arcsine function. Arcsine of 1/2 is equal to pi over 6. And the triangle told me so. Okay? So those are the kinds, that's the flavor of reasoning that goes on when we work with inverse trigonometric functions. What inverse trigonometry lets us do is it lets us discover angles. After all, the original trig functions, sine, cosine, and tangent, we feed them an angle, and they give us a ratio. And therefore their inverses are things that we can feed a ratio and it spits out an angle. What we get out of an arc function is what we put in to the original trig functions, angles. So what does this look like in another example? So it's the same kind of story here. We're given some information. We'll use a appropriately constructed right triangle to answer these questions. And because we sort of spent a lot of time talking through the example that we just did, I'm going to go through this a little bit more quickly. So let's start with a right triangle that has legs of length 11 and 13. So not quite sure what that would look like, but the legs are pretty close in length to one another, so it's going to look kind of like this probably. Legs of length 11 and 13. Let's answer the latter part of this question first. What's the length of the hypotenuse? Well, again, we'll use the Pythagorean Theorem. 11 squared plus 13 squared is equal to c squared. 11 squared is 121. 13 squared is 169. Add those together and we get 280. No, 290. I think that's right. And so c is going to be the square root of 290. Let's see. And I don't think we can actually simplify that any further. Square root of 290. That is a square-free integer. And so the best we can do is just leave it like that. And then the question is, what are the measures in radians of the non-right angles? So let's label them. let's give those angles names. Let's call them, I don't know, alpha. I'm going to color code these. Call them alpha and beta, the Greek letters for A and B. And so to answer this question, what are the radian measures of those angles? All that we really need to do is pick any trig function that we like. Any one of sine, cosine, or tangent, right? Because we can get the values of sine, cosine, or tangent out of ratios of the lengths of the sides of this right triangle. So pick any trig function, and we know all those lengths, which is the key here. Pick any trig function of alpha or beta. Let's suppose that I pick, I don't know, cosine once, and then maybe I'll pick tangent for the other one, right? So cosine of one of them, tangent of one of the others. And let's suppose that I choose cosine for my alpha, and maybe I'll pick tangent for beta. Again, I can do this with any trig function that I like, and because we know all three sides of this right triangle, whichever trig function we pick is going to determine which ratio we have to compute of the lengths of those sides. But any one of them will serve. They'll all give us the same answer, which is the great part about it. So let's suppose that I choose cosine and tangent like this. What is the cosine of alpha going to be? Well, cosine, remember, is the ratio of adjacent to hypotenuse. And so all I have to do to figure out what the cosine of alpha is ask what's the length of the adjacent side to alpha. The adjacent side to alpha is that leg of the right triangle, not the hypotenuse, which shares one of the rays of the angle A, angle alpha. And so that adjacent side is 11. So 11 is the adjacent. My hypotenuse of my right triangle is, of course, the square root of 290. And so whatever alpha is, its cosine is equal to 11 over the square root of 290. So when I plug alpha into the cosine function, it spits out this 11 over the square root of 290. So if I want to know what alpha is, what's the measure of the angle alpha, I just have to use the inverse of the cosine function and put into that inverse 11 over the square root of 290, right? In other words, what I'm really doing is trading places between the input and the output to this cosine function. And when I trade places between the input and the output, my function, which was originally written cosine, is now arc cosine, the inverse function of cosine. And the input to this function is the output from my other function, 11 over the square root of 290. And the output from this function is the input from the old function, which is my unknown, heretofore unknown angle, alpha. And so alpha is the arc cosine of 11 over the square root of 290. And so when I, or the author of this problem say, give an exact answer, this is what we mean by an exact answer. Alpha is the arc cosine of 11 over the square root of 290. But of course, if we want an estimate of this, probably what we'll do is we'll use some technology, because I certainly don't know how to compute an arc cosine of 11 over the square root of 290. So I will just open up a graphing calculator, say, like Desmos, and just write in here, arc cosine of 11 over the square root of 290. And it will spit out an approximation for me. And by default, Desmos spits these out in radians, so about 0.8685 for however many decimals you like. And then that's, again, radians. And so there is an approximation for this angle, right? It's about 0.86854 radians. If I wanted to know how many degrees, I would just have to convert that into degrees. And the conversion factor, as always, is that there are pi radians for every 180 degrees. So to go from radians to degrees, we have to multiply by 180 and divide by pi, and it's about 49.8 degrees. 49.8 degrees. So if you really wanted degrees, you could always have set your calculator into degrees mode before evaluating that inverse trig function as well. And then real quickly for beta, Well, we can take a shortcut for beta, right? Now we know what the measure of angle alpha is, and we know what the measure of this angle right here is. This is 90 degrees, this is about 50 degrees, 49.8. And we know that all three angles in a triangle, a Euclidean triangle, are going to add up to a total of 180 degrees. So what we could do is find our other angle that way, 49.8 plus beta. So beta is the one that I don't know, plus 90 degrees. That's the measure of this right angle that's right there. That those have to add up in total to 180. And so I'll just take 180, I'll subtract 90, and get 90 degrees equals 49.8 plus beta. Then I'll subtract 49.8 from 90, and I'll get 40.2 degrees. So at the end of the day, beta is going to have an approximate degree measure of 40.2 degrees. But of course, that's kind of missing the point of this problem, because we also wanted to use inverse trigonometry to arrive at the same conclusion. So let's just do that for the practice. What would the tangent of beta be? Well, the tangent of an angle in a right triangle is the ratio of the opposite side to the adjacent side. And so for beta, the opposite side to beta is 11 in length, and the adjacent side is 13. And so the tangent of beta is 11/13. And therefore, beta, again, interchanging the roles of input and output from the tangent function. The output was 11/13, the input was beta. If I switch those two, then beta becomes the output, 11/13 becomes the input, and the function becomes its inverse, namely arctangent. Arctangent of 11/13. And so again, if we are wanting to be absolutely sure, we'll evaluate arctangent of 11/13 using technology. And I get about 0.702 radians. Convert that to degrees by multiplying by 180 over pi. And sure enough, there's my 40.2 degrees that we were predicting in the first place. Okay. So approximately 40.2 degrees. So that is the benefit, that's the reason for being of inverse trigonometric functions, because trig functions themselves turn angles into ratios. Their inverses can turn ratios back into angles as a way for us to discover the measurements of angles when what we know are the measurements of lengths that surround them, right? That's the real practical sort of geometry use for inverse trigonometry. When we push a little further into our last section of trigonometry for the semester, that's the section on identities and equations and solving equations that involve trigonometry. Same story. When we solve a trigonometric equation to get a variable that used to be inside of a sine, cosine, or a tangent, solving that equation is going to let us discover the value on the inside, but we need inverse trigonometry to undo the regular trigonometry that is trapping the variables that we don't know. So that's where we're going to leave it for today. When we come back in our next session on Wednesday, we're going to pick up on the discussion that we had about powers of x and push it forward to talk about polynomials and how what we learned today about the local and the end behavior of power functions of x can inform the local and global behavior of polynomial functions as well. You won't want to miss that. Polynomials have a very long story in mathematics. And so now that we know enough to do that analysis, we're going to move on to that second section of Chapter 5 when we come back. I hope you're all doing great. You had a great weekend, and I will see you around at our next class.